Hello, this is the presentation of unsupervised learning techniques for class 3. It is for course number EEL 6825, pattern recognition. To start, this presentation goes through three distance-based clustering techniques. They are k-means clustering, hierarchical clustering, neural networks, self-organizing maps, and two probability-based clustering techniques. They are fuzzy C-means clustering, Gaussian mixture models. External validity indices are used to measure the extent to which particular cluster labels match the other class labels, and the internal validity indices are used to measure the goodness of a clustering structure without respect to external information. Now, the purpose of this project is to find the optimal number of clusters for each clustering techniques given the certain type of dataset. Here, we choose the dataset previously preprocessed and stored into a MAT file, which is simulated to reflect characteristics of chips. In this case, it should be sufficient to select manufacturing process, thermal design power (TDP), and the rating features to cluster the dataset. We can see that chips with smaller process have lower TDP, and vice versa, as one may expect. Now we are going to explain a little bit about three distance-based clustering techniques. First is the result for k-means clustering, KC. It is a partitioning method which partitions data into k mutually exclusive clusters and returns the index of the cluster to which it has assigned each observation. It uses an iterative algorithm that minimizes the sum of distance from each object to its cluster centroid over all clusters. We use cosine distance measure here. Second is the result for hierarchical clustering, HC. It groups data over a variety of scales by creating a cluster tree or dendrogram. The tree is not a single set of clusters, but rather a multi-level hierarchy, where clusters at one level are joined at clusters at the next level, which means each cluster may have subclusters. This time, we use Spearman distance measure and weighted linkage method. We are able to judge clustering visually by plotting its similarity matrix. If we have well-separated clusters, then if we reorder the similarity matrix based on cluster labels and plot it, we would expect it should be roughly block diagonal, like this. Next is the result for neural networks, self-organizing maps, SOM. It learns to classify input vectors according to how they are grouped in the input space, for both the distribution and the topology of the input vectors they are trained on. The data points are divided into non-overlapping clusters, such that each data point is part of exactly one set, just like k-means clustering. We can make use of the interactive tools to set up, train, and test a neural network. It is then possible to auto-generate the code for the purpose of automation. To get an idea of how well separated clusters are, we can make use of silhouette plots, which displays a measure of how close each point in one cluster is to points in the neighboring clusters. The measure ranges from +1, indicating points that are very distant from neighboring clusters, through 0, indicating points that are not distinctly in one cluster or another, to -1, indicating points that are probably assigned to the wrong cluster. Here, we are going to explain a little bit about two probability-based clustering techniques. First is the result for fuzzy C-means clustering, FCM. It is a data clustering technique wherein each data point belongs to a cluster to some degree that is specified by a membership grade. It returns a list of cluster centers and several membership grades for each data point, which iteratively minimizes the sum of distance of each data point to its cluster center weighted by that data point's membership grade. We can have a 2D and 3D view of the membership grades between different clusters along two dimensions, namely manufacturing process and rating. Last one is the result for Gaussian mixture models. Now it is very similar to fuzzy C-means clustering, known as overlapping clustering technique, because while clustering, a data point can simultaneously exist in more than one clusters. It is formed by combining multivariate normal density components, which uses expectation maximization algorithm that assigns posterior probabilities to each component density with respect to each observation. The posterior probabilities for each point indicate that each data point has some probability of belonging to each cluster. Also, we can have a 2D and 3D view of the probability that a data point belongs to a particular cluster along two dimensions as well. Okay, almost every clustering algorithm will find clusters in a dataset, even if that dataset has no natural cluster structure. It is important to be able to distinguish whether there is non-random structure in the data. External validity indices are summarized in the table, which shows adjusted Rand index, Merkin index, and Hilbert index respectively. Now, how does one determine the correct number of clusters existing in the data? Let's take a look at internal validity indices. MS represents how well each data lies within each cluster. High values indicate well-matched situations ranging from -1 to +1. DI measures separation and compactness, the minimum and maximum distance between and inside data clusters. Higher values indicate better clustering. DBI is based on a ratio of between and within cluster distance. Lower values indicate better tightness and separation inside and between the clusters. Thus, the optimal clustering solution has the smallest value. CHI is sometimes called the variance ratio criterion. The optimum clustering solution has the highest value, indicating both a small within cluster variance and a large between cluster variance. KLI is based on the squared differences of all data in a particular cluster from their respective cluster centers. The optimum number of clusters is the one that maximizes the values. HI is a crude rule of thumb, suggesting that the best cluster partition is obtained by splitting one of the clusters. Similarly, the optimal number of clusters is the one that maximizes the value, which also should be less than a given threshold. Now, we will have a quick demonstration of the program, and you can see just very basically. Import data here and set the random number seed to make the results repeatable in this script. Select features to use for clustering. Apply the k-means clustering and hierarchical clustering. Visualize their similarity matrix. This part uses neural networks self-organizing maps and plot its silhouette values by creating 3 clusters. Apply the fuzzy C-means clustering, show probability plots, and the same to Gaussian mixture models. Finally, 4 external validity indices and 6 internal validity indices are all measured for each clustering method Separate functions are widely used in this program. I have shown all the results in the PPT as you have seen. Okay, in summary, we can conclude that FCM and SOM have the highest similarity, while FCM and HC have the lowest similarity. Moreover, HC and KC, HC and SOM and GMM have almost identical similarity, which also the same to KC and SOM and KC and FCM. 5 clusters is the better solution for KC and HC. 7 clusters is the best solution for SOM and FCM, and 4 clusters is the optimum choice for GMM. That's pretty everything. Thanks for your time.